all that awesome paragraph that I typed up, but I'm going to just simplify it as the lines coming off of the softball, where that guy's hitting that softball. These are vectors. They look just like rays, but they do not act like rays. If you remember from geometry, a ray was something that had a start point and went on forever. Vectors do not go on forever, they just stop right there. And length is very important to vectors, and so is the direction in which it's going. So we can see this bat. He hit one ball at 45 degrees. That's why one vector is at 45 degrees past what kind of that origin line would be. The other ball was hit at 20 degrees. That's why that vector is at 20 degrees. Notice one is longer than the other. That is not how far the ball traveled, because unless we're playing a very weird game of softball, softball does not just stop in the middle of the air and then just fall down or something. The length of this tells you how hard the ball was hit. Look how much longer the 60 feet per second is versus that 30 feet per second. This ball was hit twice as hard as the 30 foot per second one, and that means that this vector is actually twice as long. So because it's twice as long, it tells you it's hit twice as hard. But that's just kind of an idea of what vectors are and what you can use them for. We're going to get less into what you can use them for force. We're going to do a little bit of application, but this isn't a physics class, nor is this calculus. So we're going to stay away from the physics problems for the most part. We'll have some kind of basic physics problems, but nothing crazy for those of you that just fear physics in general. It won't be that bad. Okay. But we're going to get into what a vector is and what important stuff I need to know about it. So the first thing I'm going to do is I'm going to draw a vector on the left-hand side here. Just a vector, looks kind of like a ray. Isn't a ray, but it looks like a ray, and I'm going to call it a B. I'm going to call it AB. Now, if I'm trying to describe this to someone, and I don't want to have to draw that line every single time, and I want to say which one I'm talking about, you're just going to it's kind of like labeling a ray in the fact that you just write AB and you put a vector above it, and that tells you you're talking about vector AB. The other way we can label it, and this is usually done in books just because of how hard it is to bold something with pencil. The other way you can do it is you can take a lowercase bold letter. A lot of times we use V. And so if I put V right there, we can also use that symbol here and say, well, I'm talking about vector V. But like I said, it's really hard to do bolded letters with pencil without making it look like it looks up there, crappy. So a lot of times I don't bold it. I'll just put a lowercase v, and a lowercase v will stand for it. As long as we're all aware that I'm talking about vector v, I won't always bold it in. I will most of the time bring it up that, hey, this should be bolded. It's not going to be because I'm not typing something. But just so you know, those are our two possible symbols for a vector. Now the next thing we're going to talk about is our magnitude. Because a vector has two things. It's got magnitude and direction. That's important. Just like with that baseball, direction was definitely important of drawing it, and so was the length of the line. So magnitude is just our length. It's the length of our vector. How long is it? Some important things about magnitude. So if I'm talking about length, it must be positive. It must be positive. Joe, do you want to focus on the notes? I'm less on organizing for right now. All right, it must be positive. And so if we have, once again, our vector AB, our magnitude is this length here. And the symbol for magnitude is just an absolute value bar. So I say that is standing for vector AB. But as soon as I put absolute value bars around it, I'm saying magnitude AB. So absolute value bars automatically mean magnitude, because all I'm really saying with magnitude is length. And that's all we're going to be talking about is lengths. So as soon as I put absolute value bars on, I'm talking about the absolute value of that length, which makes it a magnitude. So think about magnitude. When I say magnitude, just think absolute value. It's a fancy word for saying absolute value of something, of some number, is our magnitude. So the hard part of vectors is I'm going to be listing a whole bunch of names and stuff. Don't get bogged down in the names. I will do my best to tell you kind of what I'm talking about as easily as I can say it. So we'll say some complex stuff, but it really just boils down to triangles and x and y coordinates. All right? So as long as you can think along those lines, you'll be okay in this section. The first thing we're going to talk about is scalar multiplication. That's pretty easy because we're going to very basic talk about it. That is on the very left-hand side, I'm just going to draw, maybe not even that big, I'm just going to draw a vector. And we'll call that vector A, B. Now once it's named in a very specific order. And that is the fact that A must be your start point, and B has to be your end point as soon as you know it's vector AB. Now, if you look above, at these two tugboats, we have two tugboats that have two vectors attached to them. Remember, length of a vector is very important. If you look at tugboat A, its vector is A. If you look at the tugboat above it, its vector is 2A. And the length is twice as long. So not only the name, but the length of it tells you how much stronger that top tugboat is than the bottom tugboat. So if you read that example, if the bottom tugboat is pulling or pushing at a force of 2,000 pounds, it means that the one above it is 4,000 pounds because A, the vector is twice as long, and it's 2A. So if I have a vector AB, and someone told me to draw the vector 2AB, I have to keep the vector going in the exact same direction, because direction is important and magnitude is important. So I have to keep it going in the exact same direction, except now it's going to be twice as long. So in other words, if I did half of it, that would be my AB, and the other half of it would be another vector AB. We could do half vectors. We could do half vectors, which would just be half the length. So we could do half of AB. Half AB is just going to be a shorter half the line, as best as you can make it half. And the final thing I'm going to talk about is negative. We can have negative vectors. I can say negative AB. And negative AB is going to be the exact same thing as AB, except it's going to go in the opposite direction. So the line's going to look exactly the same as AB, except now it's going to go down, and A is now going to be on my bottom, and B is the starting point of it. With negative AB, I just want to point out something. If you look at negative AB, that's the exact same thing as saying BA. So vector negative AB is the same thing as vector BA. And that's scalar multiplication. We'll talk more about scalar multiplication next Monday. I just want you to get a general feel of how length is important and how magnitude is important and how you can draw it to show what you're talking about. All right, the next thing we're going to talk about is adding two vectors together. I'm going to go ahead and name all of these A and B. I know they should be bolded, but I'm not going to spend a whole bunch of time bolding them. We're just going to say vector A is always going to be on the bottom. Vector B is always going to be the one on the left. I go over here and I have vector B. I have vector A, just so they're already pre-labeled. We're going to go ahead and add. We're going to add both of those vectors. So in the first one I have vector A and I have vector B. I'm going to go ahead and do A plus B. And what I'm going to use is what's called tip to tail method. So picture, I'm doing A plus B. What you're going to do is you're going to trace A out, and then you're just going to attach B onto it. So the tip of A is going to lead into the tail of B, and you're going to go ahead and mark it. So it's going to look something like this. So you carry all the way to the end of A, and you mark kind of what B would look like if I attached it onto there. And now what you're going to do is you're going to attach from where they started to that endpoint. And that line right there, or that vector, is going to be A plus B. And the next one I'm going to do B plus A. If you can kind of picture that in your head, you're going to see that's going to be the exact same vector. It's just going to be a different route of getting there, because this one's B plus A. So we're going to go to the tip of B, and we're going to do a vector A right there. And where that ends is where I'm going to draw my new vector. There it is. And this one's B plus A. So no matter which way I added it, I ended up drawing the same vector. It was just this is a different way to get to the exact same vector. But if I asked you what's A plus B and you just drew this, you're fine either way. The trouble comes in when you're doing subtraction. Subtraction matters what order you do stuff in. You won't have the same answer. For this one, I'm going to do B minus A. Well, B plus A would look something like this. That's B plus A. But I don't want B plus A. I want B minus A. So instead of doing a positive A, I'm going to do a negative A from the tip of that one. So this is actually negative A. It's A, but it's going in the opposite direction. That's what makes it a negative A. Well, now we connect the vector to it. And this is going to be B minus A. However, if I did, I'm not going to on here because it makes it kind of a muddled drawing. If I did A minus B, you can kind of picture I go out to A, and B is going to come in like this. So it's going to end up being kind of a straight line, but the answers are different. With adding, they go to the same place. With subtraction, they do not. So be very careful when you're doing subtraction. I could also do A plus half of B. In that case, you'd go out to A and just do half of B. All right? So it's just drawing is what this kind of method is. Tip to tail is just drawing. All right, so that is vector addition. Now we're going to get to some confusing terminology, but all I'm talking about are x, y values. So I always think back at what I'm actually talking about. So if I give you a vector, W, and I'm going to let this R stand for my magnitude, so that is the length of W. In fact, any hypotenuse is always going to be our magnitude, in fact. So I'm going to go ahead and star that. I'm going to say, hey, just so you know, R is going to equal the magnitude of that line. And if you're really interested in notation, you put absolute values around it, but you don't need it as soon as I say that equals our magnitude. All right, so that equals our magnitude. Well, if you look at that vector, it moves in a 2D plane, which means on like an XY plane, it needs to move horizontally, and it's going to move vertically. So if I was going to walk to this point, and I'm not allowed to walk at diagonals, I'd walk right, and then I'd walk up to get there. This is my horizontal movement, and this is my vertical movement. So we're going to call our horizontal movement WX, and that's why I have it kind of drawn. Let me see if I can get my arrow tool. So WX is my horizontal movement. W sub x, well, that's just a regular x value. If I have an XY plane, this would be my x value, right? If this was 5, if WX equals 5, it'd just be x equals 5. Now we move up. well, that's really my y value, and all we name it here is our w sub y. And I'm going to label it this way because do you see that right triangle I created? Because I created a right triangle, you're going to immediately think SOHCAHTOA. You're going to think sine, cosine, tangent, so on and so forth. So the first thing, and in fact we're only going to talk about sine and cosine in this one because it's going to develop two formulas that are going to help us. The first thing I'm going to talk about is cosine of, do you see that theta I created there? There's theta of my triangle. So if I take cosine of theta, cosine equals adjacent over opposite, which in this case, my adjacent is going to be w sub x, over my hypotenuse, which is r, which is also my magnitude. So whenever I say r, think magnitude. But magnitude is just that distance. Well, manipulating this formula just a little bit, I'm going to get that my horizontal movement, or my horizontal component, is just going to equal my magnitude. Remember, r is my magnitude, times the cosine of whatever angle that's at. So if perchance there's a problem, like example number 1, that gives you the magnitude and the directional angle, you can then plug it in to figure out your horizontal, or kind of think about it as your x value. It's just your x value. All right, using that exact same idea, we're going to use sine of theta. Well, sine is opposite over hypotenuse. Our opposite is now kind of our y value, our horizontal, our vertical component, over magnitude, which rewriting that is going to be my vertical magnitude, or my vertical component is going to equal r times sine of theta. In other words, how far right did I move is going to be dictated by my magnitude times cosine. How far up did I move, or my y value, is just going to be r times sine theta. In other words, I have a right triangle, and I'm just solving for a piece. So if I drew this right triangle, I said solve for w of x, you'd say, well, I'm going to use cosine. And that's exactly what you'd get. I'm just solving for a piece. Now, down here, we're going to write the formula. A lot of times, I'm going to ask you for the magnitude of the horizontal component. So this is my magnitude of my horizontal. That's going to equal the absolute value of r times cosine theta. Likewise, there'll be times I ask you for the magnitude of your vertical, which is going to equal the absolute value of r times sine of theta. These are good things to have memorized. If I talk about horizontal, you should think about cosine. When I say vertical, you should think of sine. It makes your life a lot easier, rather than having to solve a right triangle every single time you do one of these problems. All right, any question about either one of those two formulas?
Wait, magnitude
Of horizontal. Sorry. I guess I could write it all in. Which would make this one the magnitude of our vertical. So these are our horizontal and vertical values. If I take the absolute value of it, it becomes the magnitude. Magnitude is just say, take the absolute value. All right, so if you can find your horizontal value and you take the absolute value of it, that is your magnitude. Absolute value, magnitude, go hand in hand. Do you want me to leave that up for just a second? We're good? Yeah. Okay, so the first problem is relatively easy if I know that formula. So that first problem we got here, it says find the magnitude in horizontal and vertical components for vector v with magnitude 8.3 and directional angle 121.3 degrees. I'm going to go ahead and draw this really quick, just so you know what I'm talking about, because this is kind of our first vector we've ever drawn. So they're saying this angle happens at 102 or 121.3 degrees, which might be about here. And then the vector itself would come out right at the edge of that. And that length is 8.3. So now they're just asking for what is this distance and what is this distance. If I'm walking there and I have to go left, to how high do I have to go to get there? That is our... So you could draw a right triangle, solve that right triangle for those two parts, because we know the hypotenuse is 8.3. But for someone that knows those two formulas, it's going to go a little quicker. They're going to go, well, I know my horizontal is going to be W sub x, absolute value, equals the absolute value of my magnitude, which is 8.3, times the cosine of 121.3 degrees. I should put that in parentheses so stuff that I get mixed up. Just like the vertical, and they did ask for the magnitude, that's why I'm putting it did ask for the magnitude, so that's why I'm putting it in absolute values. My vertical component is W sub y equals 8.3 times 121.3 degrees. I forget these actual values. Let me go ahead and put them down. So my horizontal component, which is 8.3 times the cosine, that's going to be 4.3. And the magnitude of my vertical is going to be 7.1. So those are my two answers.
Wait, for the vertical,
yeah.
Isn't there supposed to be a sign here? Or?
Yeah, I said it, I just didn't write it. You are 100% right. Let me write that in there. Because that wouldn't make any sense otherwise, right? I said it, I just didn't write it. So it should be the sine of 121.3 degrees. Now it's going to equal that 7.1.
Is there a unit or is it just some?
It's just going to be 7.1. Because they said the magnitude is 8.3, so they didn't give me what that 8.3 is. If it was 8.3 feet per second or something, then you might have to. But for us, we're going to be okay not putting units on these. It was a great question, though. All right, so that's it. When you think horizontal component, think cosine. When you think vertical component, think sine. That's the big difference between those two. Everything else is just the magnitude and the directional angle. All right, does that make sense? They're not hard if you know the formula or you know how to solve triangles. As soon as you make it more complex than it is, then it becomes really hard. If you get bogged down in horizontal component, vertical component, you got to think horizontal component, that's just your x value. Vertical, that's just your y value. All right. And in fact, to confuse you just a little bit more, we have component form. Component form is just asking you, what is the value at this point? Now, you would think, well, if I was on the xy plane, don't write this. You would just say, well, that's just my x, y. Whatever my x value is, whatever my y value is, that is that point. But thank God we're in vector world, where we warp things just a little bit, and this is how we write that exact same information. That point right there, AB, is our component form. So we do not use parentheses. We use the little arrow brackets, and that is my component form. But don't confuse this stuff, okay? This is the exact same thing as W sub x, which is the same thing as my x value. This is the same thing as W sub y, which is just my y value. These are all different terms for the same thing you know. You know how to find x values, you know how to find y values. These are just different names for it. All right. I want you to notice that the vector creates a right triangle. Vectors always create right triangles. That's how we do all of these formulas. It does create a right triangle, and let me go ahead and draw that right triangle. And that right triangle is composed of my magnitude. I'm going to call that R. That's my magnitude still. Our horizontal is A, which is, remember, the same thing as W sub x. They're the exact same thing, exactly the same thing. And my B is my vertical component, which is exactly the same as w sub y. These are all the same things. So if you interchange these letters, I'm not going to take any points off. If I ask for the horizontal component and use a or b instead of w sub x, I'm okay with that. If you use x and y, I'm okay with that too. I just want the right value. So based upon this triangle and the fact that we know the Pythagorean theorem, we can say that a squared plus b squared equals c squared, which is actually my r in this case, because my hypotenuse is r. Once again, if I know b and r, I can solve for a. If I know a and b, I can solve for r, and vice versa. Most of the time with this formula, we're going to be solving for the magnitude. So magnitude is going to equal a squared plus b squared. And since it is a magnitude, it's always going to be positive. So this is my magnitude equals my x value squared plus my y value squared, take the square root of it. And in fact, that's the first thing you're going to have to do on the next side. If you're there, I'm going to leave this up for just a second for people still copying. The next side says calculate the magnitude, and it also wants the angle of that vector. Always start with finding your magnitude. It's easy, the easiest to do, and that way you can save yourself for getting it wrong or something. So the very first thing I'm going to do is I'm going to go ahead and find the magnitude. Scratch that. The very first thing is not finding the magnitude. The very first thing you're going to do is, if I tell you my vector ends at -2, -5, you are going to draw it. You are going to just draw it every single time until you're 100% sure you can get it in your mind, because I can't tell you it's got to be like 25% of people that got these problems wrong. As soon as I asked them to draw it, got it right after they drew it. They just were too lazy to draw it. All right, so the first thing is magnitude. Magnitude is what is this length of this line. You can either use the formula, or you can create a right triangle and actually solve for this. Your choice. I like using the formula. So magnitude is just r equals the square root of a squared plus b squared, which is going to go ahead and equal the square root of -2 squared plus -5 squared, which is going to equal the square root of 39. Once again, it is not 39, it is actually 29. But once again, it is positive because it's a magnitude. So all this 29 is saying is I can throw a 29 here and say this distance is 29. Magnitude is pretty easy. It goes pretty quick. Directional angle can be a little more difficult. Like I said though, everything we do with this, with vectors, is right triangles. So if you're not sure how to do something, draw a right triangle. And if you remember from when we did the sine and cosine where we find values of stuff, we're always going to connect our triangle to the x-axis. That is a triangle. And not only is that a triangle, I know the two sides of that triangle. I know one is -2 in length, and I know coming down is -5. I also know that this is square root of 29. I'm not going to put it on there, because generally I use the values that are given to me just in case I got that one wrong. I'm just going to use the -2 and -5. Well, note, I'm looking for this entire angle here. How much is from here to here? 180. So I'm not actually looking for that. I'm just looking for this little extra bit that I'm not sure of. I'm going to go ahead and call it, maybe I won't write it right over it. I should put it over here. I'm going to call it alpha. I'm going to use alpha to help me solve the big one. Well, if I look at alpha, -5 is across from it, and -2 is adjacent to it. I'm going to think of SOHCAHTOA, and I'm going to think of which one has adjacent and opposite in it. Yes? Oh, there we go.
Would you use the tangent inverse then?
Yeah, you're going to end up using the tangent inverse. Perfect. I'm just going to start with the tangent. Tangent of alpha equals, tangent is TOA, so that's opposite, which is -5, over -2. But just like Ahmed said, I have to take the tan inverse of both sides. 5 over 2 is just going to be 5 over 2, not negative, because a negative divided by a negative equals a positive. So alpha is going to equal about, I think it was 68.2. Yes, 68.2. So here's the difference between someone that wants perfect score and a person that wants a point off on this one. The person that wants the full points is going to say, well, I drew it. I know that this complete angle isn't 68.2 degrees. I know I need to add 180 to it to actually get my theta. So theta is going to actually equal 180 plus 68.2, which is going to be 248.2 degrees. This person gets full points. This person gets -1 because they didn't draw it or understood what they're actually looking for. They're just plugging numbers in an equation because Mr. Pavian showed it on the board. I want you to know what angle you're actually looking for. You're looking for the full thing. So in this case, I added 180, correct? There will be times where you do 360 minus that angle. There will be times where you do 180 minus that angle. You have to look at what you're looking for and what they gave you, what this tangent gives you. You got to be smarter than the problem. Tangent doesn't always get you exactly what you want. You just have to use it to get exactly what you want. So either it's adding, sometimes they'll give you the exact answer. If I had an angle right here, it'd give us the exact answer. And we don't have to add or subtract. But just be careful, you have to add or subtract on a lot of those. Alright, but that's how you find magnitude and angle of a vector. The last one goes really, really quick. It says find the component form for a vector of magnitude 40 miles per hour, and an angle of 330 degrees. So just remember that component form is our A, comma B. But A is just our horizontal, and B is our vertical. So when you're thinking A, you can really think of W sub x. They're the exact same thing. If I ask for A, I'm actually asking for W sub x, which is the exact same thing as your x value. If you look at the other side, W sub x is going to be our magnitude times the cosine of theta. And that means B is going to be my W sub x, or W sub y, which is going to be my magnitude times sine of theta. In this case, our magnitude is 40, and the angle we're talking about is 330 degrees. Here, once again, our magnitude is 40. This time we use sine of 330 degrees. The only one to remember is this one is -20. I don't remember the other one. Let me walk over there and get it. The other one is going to be 34.6. If I just did this, I lose half a point. I lose half a point. To finish this problem off, I actually have to write it in the form 34.6, comma, -20. And that should be more of an arrow. So you have to put it in that form to be 100% correct. All right, questions on that?
Thank you so much.
Questions, comments?